Hello everyone and welcome to my channel. Today I would like to bring you another problem from Herbert Goldstein's book Classical Mechanics. Specifically, we are going to solve problem 115 from the first chapter on fundamental principles. The main goal of this problem is to familiarize ourselves with the coordinate transformation between Cartesian and spherical coordinates. It can be helpful for those who are not very familiar with these types of calculations to watch a previous video I made on how to express kinematic quantities such as velocity, acceleration, position in the different coordinate systems, Cartesian, cylindrical, and spherical. Nevertheless, we will perform the necessary calculations here, but we will go through them a bit quicker. So without further ado, let's get started. The problem states as follows. A point particle moves under the influence of a force derivable from a generalized potential of the form capital U depending on r vector v vector velocity equal capital V depending on the radial coordinate plus scalar product of sigma and capital L, where r is the radius vector from a fixed point, capital L is the angular momentum about that point, and sigma is a fixed vector in space. Quantum enthusiasts might have recognized immediately this term as spin orbit. And the problem asks A, find the components of the force on the particle in both Cartesian and spherical coordinates on the basis of equation 158 of the book. B, show that the components in the two coordinate systems are related to each other as in equation 149. And finally, obtain the equations of motion in spherical polar coordinates. The first thing we notice is that the potential consists of two terms, one quite familiar in the radial coordinate, capital V, which gives rise to central forces, and another dependent on spin, sigma, and angular momentum. Let's work on this term. The first step is to choose a direction for the sigma vector and angular momentum. In the most general case, they are not parallel and form an angle, let's call it theta. Without loss of generality, let's assume the direction of the sigma is along the z-axis. The problem asks to find the expression for the components of the force derived from the potential in Cartesian and spherical coordinates. Let's start with Cartesian coordinates. The potential depends on the radial coordinate r, which is simply the square root of the sum of the squares of the Cartesian coordinates and a term involving angular momentum, which is the cross product of position and momentum, that is, mass times velocity. So we are left with this expression here, dependent on the cross product of position and velocity. If we expand the cross product in Cartesian coordinates and focus on the z component, since we have assumed the sigma vector along the z-axis, we get this expression here. It is easy to perform the cross product and take the z component. It is simply the term in ux multiplied by the term in uy, and it gives x y dot, minus the term in uy multiplied by the term in ux, and gives y x dot. And so we obtain the potential in Cartesian coordinates. Capital V depending just on the radial, that is the square root of the square components, plus m sigma z x y dot minus y x dot. We are asked to find the force that there is from this potential. According to equation 158, the generalized force derived from the potential are calculated using the following formula. Qj, which is the generalized force, is minus the partial derivative of u respect the generalized coordinate qj plus total derivative in time of the partial derivative of u with the general velocity q dot j. Let's mention here that we are not going to focus on where this formula comes from. We will only concentrate on the calculation. Basically, in the book, it starts from D'Alembert's principle of virtual displacements and defines the term of general force in this way, encompassing the forces present in the system. In the edition I used, I believe it's page 19 of the book. We see from the formula that we will differentiate the potential. So let's bring it in with the radial coordinate as the square root of the Cartesian square. We start with the generalized force in the x direction. So Qj is equal to x. The calculation is quite straightforward. We are just focusing on taking the derivatives of the potential given in the problem in Cartesian coordinates and also derivatives of the radial coordinate. Once the derivative of the radial coordinate r and capital U are carefully taken, we arrive at the expression for the generalized force in the x-coordinate, the partial of capital V, the central potential, with the radial coordinate, multiplied by x divided by r minus 2m sigma y dot. The calculation is completely analogous in the y-coordinate, and the result is very similar. Just in this case, we have x dot and y divided by r. And for the z coordinate, it's somewhat simpler since we don't have terms that derive from the sigma angular momentum summand, as it doesn't depend on z and z dot. And after these derivatives, with this now, we have the generalized force in Cartesian coordinates. To be rigorous and have everything in Cartesian coordinates, we would need to substitute r with the square root of the square components. But to avoid writing more, we will leave it as it is and indicate accordingly. To find the forces in spherical coordinates, the first thing to do is to express the generalized potential in spherical coordinates. This is simply done using the transformation relations between Cartesian and spherical coordinates. If any of you are not familiar with these coordinates, I made a video on this channel, as I mentioned, about coordinate transformation and their relations. Even so, let's quickly go over this transformation. The transformation equations are as follows. The generalized potential in Cartesian coordinates was this, involving this term in sigma x y dot minus y x dot. Then we simply need to find the derivatives of x and y with respect to time, carefully applying the chain rule since r, theta, and phi all depend on time. And then this term, the sigma term of the potential becomes this. The calculation is quite straightforward. Many terms cancel out. And in the end, we are left with r squared, sine squared, phi dot squared. So the potential in spherical coordinates is u equals v, capital V, depending just on the radial coordinate, plus m sigma r squared sine squared phi dot. Once we have the generalized potential in spherical coordinates, to find the forces in spherical coordinates, we only need to take the derivatives we learned at school. The only difficulty is to substitute the coordinate qj appropriately. And so we have the radial force. We see that the potential does not depend on r dot, so this term cancels out, and we simply have this here for qr. The potential also does not depend on theta dot, so this term cancels out, and q sub theta just becomes this. Also, we see that capital V just depends on the radial, so we don't have, like before, partial of V with theta because it doesn't depend on theta. And for q phi, the potential does depend on phi dot. So that term of the total derivative of the partial of u with phi dot doesn't cancel out. So we will need to differentiate with respect to time in r and theta using the chain rule. However, these are elementary derivatives without any difficulty. But u doesn't depend on phi, so that term in this case cancels out, and we are left with this. 2m sigma r sine of theta plus, what is in parentheses, r dot sine of theta plus r cosine of theta, theta dot. With this, we have finished part A of the problem, which was to express the forces derived from the potential in both Cartesian and spherical coordinates. In part B, we are asked to verify that the components of the force in both coordinate systems are related to each other through the following expression. Qj, the generalized force, is the sum over I f sub I multi-scalar product with the partial derivative of the position vector of the I particle with respect to the generalized coordinate qj. Here the summation extends to the number of particles, but since we only have one, the index I does not vary and is equal to 1. For the force, for simplicity, which we will see shortly, I have taken the force in Cartesian coordinates and the qj then refer to the spherical coordinates. J will equal 1 for the radial coordinate, j equal to theta, and j equal 3 for phi. Let's obtain the forces in spherical coordinates from Cartesian coordinates. To do this, we will express both the force and the position vector in Cartesian coordinates. The force here in Cartesian is this, and the partial of the vector position with respect to the generalized coordinate qj is simply this vector here. And if we perform the scalar product of this is simply fx partial of x qj plus fy partial y qj plus fz partial z qj. You might wonder what the force in Cartesian coordinates is, I mean the F. Well, is one we found earlier, the generalized force in Cartesian coordinates. We can easily see this if we let the index j run in the Cartesian coordinates. For example, if j equals x, we have that the derivative of x with respect to x equals 1, and the other two cancel out. So we have that qx is simply fx. If j equals y, this term here equals 1, and the other two cancel out, and we are left that qy simply is equal to fy. And if j equals z, partial of z with respect to z is 1, the other two cancel out, and qz equals fz. So all right, let's find the generalized force according to the radial coordinate r. We just substitute j with r and perform the necessary derivative. Let's bring in the transformation relationship between Cartesian and spherical coordinates, along with the generalized Cartesian forces we calculated in part at the beginning of the problem. So we begin by substituting fx with this expression here, taking into account that now we express x and y dot in spherical coordinates. Y dot in spherical coordinates. We also previously calculated I dot, which is the derivative of the coordinate I with respect to time using the chain rule, keeping everything in spherical coordinates. And the partial derivative of x with respect to r is simply this from the transformation equation. Fy we calculated before was this. So Fy equals this, x dot, and the partial derivative of y with respect to r is simply sine of theta sine of phi. And fz, which is a bit simpler since it doesn't have the term in sigma or the time derivative of coordinates, simply this, and the partial derivative of z with respect to r is cosine of theta. It might seem more cumbersome than it really is. The calculations are lengthy because they involve derivatives, but they are simple. The only complexity is applying the chain rule. Otherwise, it's the derivative we learned a long time ago. Take your time to pause the video if you want to review the calculations at your own pace, but as I mentioned, there's nothing particularly tricky about them. So let's move on. Now it's time to do the usual steps, factor out the common terms and tidy up the expression a bit. After doing this, we arrive at the generalized force in R, which is this, which we can see is the same expression we obtained in part A by deriving the potential. The calculation of q theta is exactly the same. The only thing that changes are the derivative of the Cartesian coordinates with respect to the angle. After some algebra, we arrive at the same expression for q theta we obtained from the potential, which was minus 2m sigma r squared sine of theta cosine of theta fiddle. And finally, for q phi in this case, the derivative of z with respect to phi is 0, but the calculus are completely analogous. And after some algebra, carefully doing the calculations, we obtain the same expression for q phi than we obtained from the potential in part A. It can indeed feel daunting at first, grouping sines and cosine squares where some terms cancel out, others sum to 1, but in the end, everything tidies up neatly and concisely. With this, we conclude part B of the problem, which required us to see that the generalized forces in the two coordinate systems are related in this way through the dot product of the force and the derivative of the position vector with respect to the generalized coordinates. Lastly, let's calculate the equations of motion. Why do we want the potential and hence the forces if not? To know how the particle will move, how it will behave. Classical mechanics is deterministic. It predicts how a particle will move in the future based on the equations of motion. And the first thing we will do is construct the Lagrangian and then solve Euler-Lagrange equations in spherical coordinates. This can be easily verified given L equals T minus U, and as long as the generalized forces Qj are obtained from the potential U in this manner. It is not difficult to prove. It's a way to check if we have correctly obtained the generalized forces, since the equations of motion have to match in both cases. Kinetic energy in spherical coordinates is obtained from the square of the velocity in spherical coordinates. As I mentioned in the earlier video, the calculation of velocity in spherical coordinates is done at least once in a lifetime. Then it is either noted in a formula sheet that we carry in our mathematical toolbox, and eventually one ends up memorizing it. We subtract the potential energy and we have the Lagrangian. So let's start with the radial coordinate. If we differentiate the kinetic energy, we obtain this part here. And we bring in QR calculated before, and we obtain the equation of motion in the radial coordinate. Now we obtain directly from the Lagrangian, differentiating the Lagrangian, and we see that both equations coincide. So what it means that our calculation of QR was correct. We proceed the same for the equations in theta. If we differentiate the kinetic energy, we obtain this part here. We bring in q theta that we calculated before. And now we obtain, to double check, we obtain directly from the Lagrangian. In this case, the central part of the potential, capital V, does not depend on the angle. And we see that both equations coincide as before, so it means q theta was correct. And we proceed in the same manner for the equations in phi. In the case of Lagrangian, differentiating the Lagrangian Euler-Lagrange equations. And here we can notice that there is no dependency of the Lagrangian in phi. So this quantity here in parentheses is conserved because derivative of time of what it is inside is 0. In this case, we say that phi, when a coordinate does not appear in the Lagrangian, we say it is a cyclic or ignorable coordinate and its canonical momentum, which is the partial of Lagrangian with the coordinate dot, is conserved. So in this case, this quantity, the canonical momentum of phi, is conserved. And phi is called cyclic or ignorable. At first glance, both equations of motion don't seem the same, but let's see that they are indeed equivalent. So let's differentiate the expression inside in the parentheses with respect to time using the chain rule for the umpteenth time in this exercise. The life of a theoretical physicist often boils down to this, differentiating, many times chain rule. Let's simply differentiate this second term carefully. We leave the first as it is, and it gives minus 2 times m sigma r dot sine square, minus 2 m sigma r square sine theta cosine theta, theta dot equals 0. And if we move it to the right side of the equal sign, we have the same equation that we obtained with the kinetic energy and the generalized force. So both equations coincide, and now we can live happily ever after. Everything coincides. Right, for the reference, in the book, the Lagrange equations derived from D'Alembert's principle are found on pages 16 to 25. The demonstration of the generalized forces Qj from the potential is straightforward since L is equal to the kinetic energy minus the potential. Thanks a lot, guys, if you've made it this far. Hope that you find it useful, though you might dream of spherical coordinates tonight. So feed your curiosity and practice mathematics. So see you in a next video, hopefully. Bye-bye.